Hello everyone, my name is Berk Erhan Yüksel. Today we are discussing the why and how the vector space concepts we discussed so far are useful in signal processing tools on applications in terms of vector space, subspace, basis, norm, and inner products, and how they relate to the signals. This course unifies the knowledge of linear algebra, theory of signals and systems, and probability theory. As can be seen from 301 and 306 lectures, we primarily interested in the set of complex numbers. This list of complex numbers will be referred to as vectors, which is suggestive of their generalization of vectors in the plane. For example, in digital signal processing, such vectors can be used to represent finite length sequences or finite duration discrete time signals. In this course, we defined signals as vectors in some vector space and systems as operators. For example, mapping between two vector spaces is an example of these operators. And in this course, we will focus on general vector spaces, which give us the ability to both formulate and solve a wide variety of problems in signal processing and more broadly in engineering and science. And we will learn how to extend our geometric intuition from real numbers to solve these more complex problems. Firstly, I want to talk about vector spaces and subspaces. And vector space V is a set of mathematical objects called vectors along with a field of scalars F. This can be real or complex, that is closed under a vector addition and scalar multiplication operation also. We can describe finite energy continuous time signals, bounded continuous time signals as vector spaces, and we can perform some mathematical analysis using these definitions in signal processing. We can overcome some problems by using vector space framework, for example, calculating an image in X-ray computed tomography and removing blur in images or noisy images and cleaning noisy observations is an applications. Therefore, we use some operations and techniques by using subspace of these vector spaces. A subspace is a subset of a vector space that is closed under the same scalar multiplication and vector addition operations. Therefore, we use some operations and techniques by using subspace of these vector spaces. For example, using intersection, union, or algebraic summation, we can manipulate these signals, and signals with a common physical or mathematical properties often form a subspace. For example, out of LTI systems, band-limited signals. This allows us, given an arbitrary signal x, to find the signal closest this has this desired property signal. On the other hand, a set of vectors are called a basis for V if this set of vectors linearly independent and their span generates a vector space V. We can weave transformation of signals as representation in different bases. We can use these definitions too much in signal processing applications, since for example, we can generate a basis for differential equations, discrete time sequences, and periodic real-valued discrete time signals, or band-limited finite energy continuous signals. Especially DTFS, a basis for discrete time sequences in this area. We define the norm as the distance between the real numbers x1 and x2. This distance metric related with also limit and convergence, continuity, open or closed intervals, and approximation. Since the norm is related to the magnitude or size of something, this can be used in signal processing applications. Furthermore, we can use normed vector space NVS applications to design finite impulse response filters, FIR filters also. On the other hand, an inner product is a mapping applications of vector spaces. The inner product of the two signals shows us the similarity between these signals. Actually, we can use norms and inner products to compare two signals to measure distance and angle between these two signals. That's it. Okay, thank you for listening. I hope you enjoyed it. Goodbye.